Hello students, I am Azizi, Professor Electronics. In our previous session, we have developed a program to run a counter manually using switch 1, which is connected on port 2.0. In this session, we will add a subroutine to reset the counter because in our previous program, there was no reset input and we will not be able to reset the value of the counter. But in this session, we will add a reset input and we will write a reset routine for our counter program. So first, we will go through our previously written program and then we'll modify our program for our new task. So let's start our today's session. And here we have the circuit which we have developed to learn the assembly language programming. And we are using 8089C51 as microcontroller, that is a member of MCS 51 family. And here we can check the value of the counter is 0. If we'll press the switch 1, that is the increment switch, we can check the counter is incrementing. And the counter value will go from 0 to maximum 255, that is FFH. And after reaching to the maximum value, that is 255, and if we'll press the switch once again, the counter value again will go to the 0 and it'll start counting again from 0 to 255. To check that after reaching the maximum value, that is 255, the counter will again go to the 0. It is not possible to press the switch for 256 times and to wait for the counter value, that is 255. It will take a long time to see what will happen if the counter will reach to its maximum value. Instead of using this switch, we'll add a clock generator here and we'll see the operation of our circuit. So we'll go to the generator mode and we'll select a pulse and we'll place the pulse here. Right click, edit properties. Here we can find we have selected a pulse. Pulse high voltage will be 5 volt and pulse width is 50%. And we can see the frequency is 1 Hz. If you use the frequency of 1 Hz, that is the time of 1 second, then our counter will take 256 seconds to reach its maximum value. But here we will increase the frequency to 10 Hz. And now the increment time will be 0.1 second. In this case, if we multiply 256 multiplied by 0.1, then the counter will take 25.6 seconds to reach the maximum value. So let's observe the operation of the counter at 10 Hz. And now we'll connect the clock generator on port 2.0. And now we'll run the simulation. Here we can find the counter is incrementing. And we will see when the counter will reach to the maximum value, that is 255 or FFH in hexadecimal. The value of the counter will again go back to the 0. Let's observe here. Here we can see the counter has started once again from the 00H. Okay, now we'll add a reset routine to our program and we'll use the switch 2 as reset switch. And here we have our previously written program which we have written in our previous session. First we'll compile this program. And here we can check 0 error 0 warning. As we have discussed in our previous session that we cannot compare the location of general purpose RAM with direct number. That's why we have moved the number into accumulator and we have compared the accumulator with the number. And here to validate the operation, we'll replace this accumulator with dbreg, which is a location of general purpose RAM. So first we'll comment the first line, that is move. So here we will comment this line and here we will replace the accumulator with db register. So we'll copy this variable from here, Control C, and we will paste it here, Control V. It means that we want to compare a RAM location with the number, that is 255. And now we'll compile our program and we will see the result. Here we can find we have an error, that is register operand expected. Here on the line 60, there is an error. And now we'll modify this program as it was in our previous session. So from here we will remove the semicolon and we will replace this dbreg by accumulator. So here we will write that is accumulator A, and here we have the original program which we have written in our previous session. And now we'll compile our program once again. And here we can find 0 error 0 warnings. It means that we cannot compare any location from general purpose RAM with a direct number, but we can use any member of the register bank, that is from R0 to R7 instead of accumulator. So here we'll replace the accumulator by R0. To check this concept, here we will replace the accumulator by R0 and now we'll compare the R0 with 255 and now we'll compile our program once again. And here we can find no error, no warning. It means that we can compare the members of the register bank, that is from R0 to R7, with any constant number, but here we will replace it with accumulator. And now we'll compile our program once again. Now we'll add another routine, that is reset routine. So here we will add another routine in our main program, and here we will write, that is call rstr, and we'll add a comment, that is reset routine. And here in switches assignment we will define another switch, that is reset switch, and we will write, that is rst switch, bit port 2.1. As we have added a new input in our program, that is reset switch connected on port 2.1, then we have to define the debouncing register for this switch also. So here we will write, that is db dly underscore reg underscore 1. In our previous program, we have written a debouncing delay of 768 microseconds, but here in this program we will learn that how to increase the debouncing delay. So we will use two registers instead of using one as we have used in our previous session, because using the single register we can have the delay of 768 microseconds. So let's see how much delay we can have for debouncing using two registers. So here we have assigned the first register, that is debouncing delay register 1, and we will write, that is EQU, and we will use the third location, that is 32H, which is the third location of general purpose RAM, and we'll use the second register, that is db underscore dly underscore reg underscore 2 EQU 33H, and we will also initialize these two registers to 0 in our initialization routine. So we'll copy these variables from here, and here in initialization routine we will write, that is move control V comma hash 00H, and we will write, that is move control V, and we'll change the name of the register, that is 2 comma hash 00H. So here we have initialized both the register for switch 2, and now we'll add another debouncing flag for reset switch. So here we will write, that is rst underscore db underscore flg, that is reset debouncing flag, and we will write, that is bit, and we'll use the second bit of the bit addressable location RAM. So here we will write, that is 01H, and we will also initialize this flag in our initialization routine. So we'll copy this variable from here, and we'll go to the initialization routine, and here we will write, that is clear control V. So here we have cleared the status of reset debouncing flag. Now we will start writing our reset routine, and here after display routine we will write the reset routine, and here we will write the reset routine, that is rst underscore r using colon, and here we will check the status of the second switch, that is reset switch. So we will write, that is jump not bit, and here we have assigned the variable to port 2.1, that is reset switch. So we'll copy this variable from here, and we will paste it here, control V, and here on this line our program will check if the reset switch is pressed, then it will jump to a subroutine, and we will assign the name to this subroutine, that is rst underscore r underscore 0. But if the reset switch is not pressed, then our program will come to the next line, and here we will write the instruction to get exit from the subroutine. So we will write, that is jump rst ext. But if the reset switch will be pressed, then our program will jump to the reset routine 0, and here we will write the reset routine 0, and we will write, that is rst underscore r underscore 0. We can assign any name as per our convenience, and here in reset routine 0 we'll compare the value of first debouncing register with 255. So first we'll move the value of the first debouncing delay register to the accumulator, and here we will write that is move accumulator, comma, and here we have the first debouncing delay register for the reset switch. So we'll copy this register from here and we will paste it here, and here we will paste the variable control V. So we have moved the value, that is dB delay register 1, to accumulator, and now we'll compare the accumulator with 255. For this we will use the instruction that is compare jump not equal. So we will write that is compare jump not equal accumulator, comma, with the number that is hash 0FFH. Here we have assigned the number in hexadecimal format, but in our previous program we have used the decimal number. Here we can find we have used the number hash 255, which is equivalent to FFH in hexadecimal number, and here we have assigned the number that is 0FFH to compare the value of the accumulator with this number. If the value of the accumulator is not equals to 0FFH, then our program will jump to another subroutine to create the debouncing delay. So here we will write that is comma RST DB DLY underscore INC. Here we have written the name of the subroutine, that is reset debouncing delay increment routine. But if the value of the accumulator will be equals to 255 or FFH, then our program will come to the next line, and here we will write that is move dB delay register 1, control C and control V, comma hash 00H, and now we'll check the second register for the debouncing delay for reset switch, and here we will write that is move accumulator, comma control C and control V, and here we'll change this 1 by 2, and now we'll compare the value of the accumulator with FFH. So here we will write that is compare jump not equal accumulator, comma hash 0FFH, comma, and here we will use the same name, that is reset dB delay increment, control V, but we will change the name using underscore 1, and here we will use that is underscore 2. In this case we are using 2 register to produce the debouncing delay for reset switch, and if the value of the debouncing delay register 2 will not be equals to 255, then the program will jump to the reset debouncing delay increment routine 2. But if the value of debouncing delay register 2 will be equals to 255 or FFH, then our program will come on next line, and here we will write that is move debouncing delay register 2, control C and control V, comma hash 00H, and here our program will move the value that is 00H to dB delay register 2. After resetting the second delay register, that is dB delay register 2, our program will come to the next line, and here it will set a flag that we have defined recently, and here we have the flag that is reset dB flag, and here on this line our program will set this flag. So we'll use set bit control V. It means that we have pressed the switch for the time that is 256 into 256 into 3 microseconds. So let's calculate what will be the time. So here we can calculate the time, that is 256 into 256 into 3 microseconds. So time will be 0.1966 seconds. It means 196.608 milliseconds. After setting this flag, that is reset debouncing flag, our program will get exit from this subroutine. So here we will write that is jump RST exit, and now we'll write the first routine, that is reset debouncing delay increment 1. So we'll copy this label from here, control V using colon, and here we will write increment in debouncing delay register 1, Control C, and we will paste it here, Control V. And after incrementing debouncing delay register 1, our program will get exit from the subroutine. So here we will write that is jump RST EXT. As a result of this instruction, that is increment dB delay register 1, the value of the dB delay register 1 will be incremented by 1, and if the value of dB delay register 1 will be equals to 255, then our program will come to this line and it will reinitialize the value, that is dB delay register 1, and it will check the second register, that is dB delay register 2, and if the value of dB delay register 2 will not be equals to 255, then our program will jump to the subroutine, that is reset dB delay register increment 2, and now we'll write the subroutine. So we'll copy this label from here, and here we will write Control V using colon, and here we will write increment the second register, that is dB delay register 2, and we will paste it here. And after incrementing the second register, that is dB delay register 2, our program will get exit from the subroutine. So here we will write that is jump reset exit RST EXT, and now we'll write the reset exit routine using colon, and here we will write that is return. If you press the switch, that is reset switch, longer than the period which we have calculated, that is 0.19 seconds, then the flag, that is reset dB flag, will be set, and in this case we will write an interlock. If this flag will be set, then our program will no more check the reset switch. So here we will write that is jump not bit reset dB flag, comma CHK reset switch, is the name of our new subroutine, and here we will start writing the subroutine, that is check reset switch. We will copy this label from here and we will paste it here, Control V using colon. If the reset dB flag will not be set, then our program will come to the check reset switch and it will check the status of the reset switch. But if the reset dB flag will be set, then our program will come to the next line and here it will check if the reset switch is released. So we will write that is jump not bit RST switch, comma RST exit. It means that if the reset switch is still pressed, then our program will get exit from the subroutine. But if the reset switch will be released, then our program will come to the next line and here we will write that is move counter REG. Here we have the counter REG, comma hash 00H, and now we'll clear the status of the reset debouncing flag. So here we will write that is clear reset debouncing flag, Control C and Control V, and after resetting this flag, that is reset debouncing flag, our program will get exit from the subroutine. So here we will write jump RST exit, and here we will organize our program, and here we can check after this instruction, that is increment dB delay register 2, we have the label that is reset exit. So there is no need to use this instruction here on this line. So we'll remove this instruction from here. Okay, delete. And now we'll go through our program and then we'll compile our program. First we have assigned the name to our program, that is manual counter program, and here we have written the variable assignments. We have used two variables in our previous program, that is counter REG and dB REG, and here in this program we have added two more variables, that is dB delay register 1 and dB delay register 2, and the hardware address for these registers are 32 and 33H, and we have added another flag, that is reset dB flag, and the hardware address for this flag is 01, which is the second bit for the bit addressable RAM. And here we have added another switch assignment, that is port 2.1, and we have given the name to the port 2.1 is reset switch, and we have modified our initialization routine. We have initialized db delay register 1 here, db delay register 2, and we have moved the value that is 00H to both the registers, and here we have cleared the status of the bit that is reset db flag, and here we have added a new subroutine that is reset routine in our main program. And now we'll go through the reset routine. In reset routine, first our program will check if the status of the reset db flag is 0, then it will go to the check reset switch, and here it will come to check the switch, and if it will find that reset switch is pressed, then it will jump to a subroutine that is reset R0, and in reset R0 our program will move the value of db delay register 1 to the accumulator to compare its value with 255, that is FFH, and here we have written that is compare jump not equal accumulator with 0 FFH and jump to the reset db delay increment 1, and in this case our program will jump to the reset db delay increment 1, and it will just increment the db delay register 1 by 1, and it will get exit from the reset routine. But if the value of db delay register 1 will be equals to 255, then our program will come to this line, and here we have written that move db delay register 1 00H. Here we have reinitialized the db delay register 1 to 00H, and after resetting the first register, that is db delay register 1, our program will come to the next line, and it will compare the value of db delay register 2 with 255, that is FFH, and here it will check if the value of the register is not equals to 255, then it will jump to a subroutine that is reset db delay register increment 2, and here it will come to reset db delay register increment routine 2, and it will just increment in db delay register 2 and will get returned from the reset routine. But if the value of db delay register 2 will be equals to 255, then our program will come to this line, and it will reinitialize the value of db delay register 2 to 0, and it will set a flag that is reset debouncing flag, and it will get exit from the subroutine. And here on the first line of reset routine, our program will check if the reset db flag is not set, then the program will go to the subroutine and check the status of the reset switch. But if the reset switch will be pressed more than 0.19 seconds, then this flag, that is reset db flag, will be set, and our program will come to the next line, and it will check if the reset switch is still pressed or not. If the switch is still pressed, then our program will get exit from this reset routine, and when the reset switch will be released, our program will come to this line, and it will move the value that is 00H to counter REG. In this case, our counter REG will be reset, and will move the value of counter REG on port, then the port 0 will also be reset, and after performing this task, that is to reset the value of counter REG, here we have cleared the status of reset debouncing flag, and from here our program will get exit from the reset routine. Now we'll compile our program and we'll check the result of our program on Proteus simulator. Here we can find 0 error 0 warning, as we have modified our last written program and we have compiled the same program, so there is no need to load the new hex file. We will just run the simulation and we'll observe the result. And here we can find the number on port 0 is 0, and if we'll press switch 1, here we can find the counter is incrementing. And now if we will press switch 2, here we can check the value on port 2 is still same. It means that we have to press the switch for a longer time, because we have used 2 registers for debouncing delay for reset switch. So we'll press the switch for longer time, and now we'll release the switch, and here we can check the value on port 0 is 0 now. It means that our recently written routine, that is reset routine, is working properly. Let's check once again. Now we'll press the switch and we'll release the switch again. Here we can check the reset routine is working properly. We can adjust the switch debouncing delay time by changing the value of these 2 registers, and if we will initialize the second debouncing delay register to a higher value, then the value of the debouncing delay will be short, and if we would like to reduce the time by 50%, then we will increase the value of second register, that is db delay register 2 to 128 or say 80H, which is equals to 128, that is the 50% of 256. and we will also initialize this register in our initialization routine. So here we will write in initialization routine, that is the move db delay register 2, and here we will write that is ATH, which is equals to 128. Now after this modification, we will have 50% debouncing delay time as we had in our previous program, and in this case if we increment the value of db delay register 2, it will take 50% time because this register is already initialized to 128 value, and it will take 128 steps to reach the value, that is FFH or 255. And now we'll compile our program once again and we'll test the result on Proteus simulator. And now if we'll press the switch 2 once again, and now we can check the debouncing delay is less than the delay which we had in our previous program. So here in this session we have learned that how to write a reset routine for our counter program, and we have learned that how to increase or decrease the debouncing delay for a switch. Now there is another assignment for you to implement a check that our counter will not exceed with a certain value. Say for example, if you would like that our counter will not increase by the value, that is 16, then we have to modify this program accordingly. It is your new assignment to modify this program and implement a check that our program will not increment after the value of 16 or any other value that we want to set for the limit for this counter. In our next session, we will learn some more assembly language programming techniques. Thanks for watching the assembly language programming course. We hope that you find this course very helpful to learn assembly language programming. If you feel that this course contributes and enhances your embedded system design knowledge, then go ahead and hit like, share and subscribe buttons, and do not forget to press bell icon to stay updated with every new upcoming video from Electro Educators as soon as it goes up. Electro Educators also offers technical consultancy in following fields. For assistance regarding technical problems, projects and any consultancy, feel free to reach out at our email address electroeducators@gmail.com. Okay, see you in next lecture.